The broadcast is now starting. All attendees are in listen-only mode.
Good morning. This is Mark Anderson, and glad to be back in the groove of providing these seminars once a week. As you know, in the sort of informal poll that was done about topics that I had shared with the partner team, there was high interest in Landsat and the remote sensing. And this was put kind of as the upfront one of the presentations because this is probably the premier example in the US Geological Survey of big data or machine learning, and that is being applied now to the images being acquired by a Landsat constellation of satellites. And I'm really privileged and proud to be able to introduce Dr. Tom Loveland. Tom is the senior scientist at AROS, the facility that is the science facility that you'll soon learn about, that downloads all these images from the satellite constellations, and they're plural, many of them. And Tom was the senior scientist at AROS for many years. Most of his career has been devoted, maybe all of it, Tom, I guess, his federal service has been devoted to the USGS. And I will say, you know, it's a lot more than just being devoted to that. Tom has been the brain trust of remote sensing for the USGS there at AROS, as well as broadly in the USGS. Just another fact that I wanted to share, and that is that back in prior to 2008, Landsat images were something you had to pay for. It was a cost. They tried to do a cost recovery basis, and that didn't work out as they imagined. But what did work out when they made all the imagery free, and you can download imagery today anywhere in the world as long as you got internet. Once those were made available for download free, that gave Google Earth their start. So if you're a regular user of Google Earth, you can thank, to some degree, Tom was in on that decision to make the imagery available. So in my humble opinion, one of the most significant breakthroughs has happened, and you'll hear from another speaker later in our series, Jesselyn Brown, on LC Map. But Tom was also behind, through collaboration with Boston University, a way of making the archive of 30-year archive of images come alive, so to speak, by comparing each individual pixel over the span of time. And again, so you'll hear from another speaker on that, but just wanted you to know that Tom was behind that. So without taking any more of his time, I'll introduce Tom and just say it was a privilege of my career to be able to serve with him there at AROS for a while and count him a friend. So Tom, it's yours.
Very good, and thanks, Mark. That was very kind of you. Good afternoon, everybody. I am Tom Loveland. I'm a recently retired senior scientist with US Geological Survey's AROS Center, and AROS is an acronym that stands for Earth Resources, Observation, and Science. And I'll talk a little bit more of that. We're located in the center of the United States, near the city of Sioux Falls, South Dakota, and we are actually some distance from the city, nestled in a corn and soybeans region that gives us some isolation that allows us to have communications with orbiting satellites without any interference. The AROS Center opened its doors in 1974, and right now we are staffed with about 630 people that carry out a wide range of activities, all related to The mission of the Landsat Earth Observing System and the operations, the archive and distribution functions, and other scientific research activities that advance that mission. And this afternoon, I will talk through examples of Landsat and of some of the things that Landsat is, our data are being used to address. Now, I just want to remind everybody, we're in the remote sensing business, and I suspect you're all familiar with remote sensing, but the textbook definition is the acquisition of information about objects without physically coming into contact with them. In our particular case, we rely on the vantage point of space and satellites that are orbiting the Earth a little more than 700 kilometers above the surface. And in those satellites, we carry instruments, collect the reflected or the emitted electromagnetic energy, and our instruments are tuned to sample particular portions of the spectrum that tell us unique things about the characteristics of the Earth's atmosphere, its lands, and its waters. Now, we actually were envisioned, the Aero Center and the Landsat program, as far back as the mid-1960s, when the director of the US Geological Survey, a guy named William T. Pecora, and his boss, the Secretary of the Interior, one of the premier conservationists in the history of the United States, started realizing that the growing activity on the defense and intelligence side and using satellites to monitor particular interests of the United States offered a technology that actually could be used for far more than that defense and intelligence purpose. And so Stuart Udall made a bold proclamation in 1966 in which he announced that he wanted to establish something called Project Eros that would use these satellites for civilian purposes to try to improve the way we manage natural resources, not just in the United States, but around the world. Now, incidentally, he also announced that NASA was going to be our partner in this venture. The complication was he really didn't have NASA's backing at the time he did it. And there was a big uproar in the federal government over Stuart Udall's proclamation. But fortunately, our Congress thought that this was a terrific idea, and so they authorized it. And here we are many, many years later, dealing with the longest unbroken Earth record ever created. Now, the idea behind Project Eros was to initiate a series of Earth observing satellites devoted to monitoring the health and the characteristics and the changes in the Earth. The first satellite that was launched on July 23rd of 1972. And it went by the name of ERTS, E-R-T-S, Earth Resources Technology Satellite. It was considered an experimental thing, but it went into orbit. 2 days later, it took its first image, and it was of the Dallas-Fort Worth urban area in the state of Texas in the United States. That basically started the clock on this continuous effort to develop or gather images of the Earth that would allow us to understand the configuration of our natural resources, their health, how they're changing, and how human development was modifying those things. Now, I want to emphasize that from the beginning, the ERTS and now the Landsat program has been a partnership between the US Geological Survey and NASA. NASA is responsible for the design and launch of the satellites and the instruments within those satellites. The Geological Survey is the operational agent. We take care of the operations of the ground system, the collection of imagery, managing the satellites as they orbit the Earth, but ultimately, most importantly, making sure all of the images collected are available to users worldwide at no cost. Now, the formal mission definition of Landsat has been steady since 1972. It is to provide global multispectral images, those samples from the electromagnetic spectrum that can be used to document and monitor global land change. We do that at a resolution that allows us to detect change that relate to both human and natural agents that are causing the change, and at a scale that allows us to differentiate what is a human modification versus a natural process. Now, our satellites are continuously orbiting the Earth, and so that affords us the opportunity to be able to repetitively, every 18 days originally, every 16 days now, see the same area on the ground with the same satellite over and over again. And so this means we have this incredible, fairly high temporal resolution record that now extends for 47 years. Over the history of the program, there have been 8 successful Landsat launches, 1 failed, Landsat 6. And so that continuation of those satellites have given us that continuity of a record that allows us to go back to almost anywhere on the Earth at almost any point in time. And there are some holes because of technology issues and data policy issues, but for the most part, we have this comprehensive global record. Those 7 satellites over time have gathered over 8.5 million images. That their collection has been done both through our institution and through international cooperators around the world. And South Africa, for example, is one of our long-standing partners in the Landsat program. But of those 8.5 million images, we distribute about 20 million of them. So same images going out many times to many people. About 20 million images are distributed at no cost to scientists and natural resource managers around the world on an annual basis. Now, Mark mentioned the fact that Landsat data are now free. Prior to our elimination of the data cost, we were distributing at our peak about 20,000 images per year, and now we're at 20 million. And so, in an hour, we're doing what we used to do in a year. So it's a testimony to the remarkable value and importance of Landsat for natural resources management. In fact, an economic study that was conducted by the U.S. government on the annual economic benefits to the U.S. taxpayer, not for international applications, but just for U.S. uses, totals about $1.8 billion a year, which is substantially more than the investment in the program. Now, because we have this repetitive record, we can go to points on the Earth and study their dynamics. In this particular case, this is an area in the Amazonian portion of Brazil, in which we see in 1984 the initial pioneering of a road into then virgin Amazon forest, the establishment of a reservoir, and ultimately the explosion of land use change related to ranching and farming. And so, our ability to quantify our impact on the Earth through these images in a very objective fashion is one of the real centerpieces of the value of Landsat. Now, as I mentioned, that we've had 7 successful launches. Here's just a handful of images of the same area along the Columbia River in the western portion of the United States, an area that has seen substantial irrigation development using waters withdrawn from the Columbia River. And as you see, for the most part, the images are very consistent in their characteristics, and that consistency allows us to do this comparative analysis over time with the confidence that every time we're looking at an individual resolution element or pixel or a field, we are comparing apples to apples. The same things, the same spectral characteristics are presented in all cases. Now, one thing I want to point out, if you look at the top row of images, that's Landsat 1, 2, and 3, and it has the initials MSS, that's the multispectral scanner, the early, the first instrument used on Landsat. Was a different technology and or a simpler technology, an early technology for imaging that is coarser in resolution and not quite as high in its radiometric and spectral quality as the modern record, which actually starts in 1983. One of the things we work hard at is making sure that the old record and the new record are comparable over time. In fact, we go to great lengths to make sure that the entire Landsat record, from that first image acquired in 1972 to the ones we're gathering today, are standardized to a consistent radiometric benchmark so that we can compare with confidence observations across the entire record. And so, what that means to you is that as you're studying, say, the changes over time in an area where you're investigating issues, you have the confidence that you're comparing very similar conditions because of this standardization of the record. Here's just a table of some of the primary characteristics of the first 7 Landsat imaging satellites. And remember, Landsat 6, I mentioned, failed in launch. What happened is the satellite was launched into space, and the covering of the satellite that's supposed to pop off as it reaches orbit failed to come off. And so the weight and the drag essentially plunged Landsat 6 somewhere in the Indian Ocean. So we've had one failure, and incidentally, that one failure occurred when NASA and the USGS were not responsible for the mission. There was a brief time when the private sector in the United States took care of the program. But, key things to take out of this. Landsat sees most of the Earth. We don't see the very top of the poles, but we come pretty darn close. The repeat cycle is now 16 days, and with 2 satellites, that means we actually can see the same area on Earth every 8 days. The imaging swath is 185 kilometers wide and continuous in its strip. The spectral properties have changed as we've advanced to every satellite, and the resolution, the smallest objects on the ground that we can resolve, has improved over time, and it will continue to improve as we move into the future. A critical part of Landsat are those multispectral measurements. Those measurements are broken into specific bands that are tailored to collect particular types of observations. For example, as you see in this, the thermal imagery, that's infrared observations at the top, are measurements of heat, which allow us to look at energy balance issues such as evapotranspiration rates on the surface. Shortwave infrared lets us look at both geological features and at vegetation moisture content. Near infrared is important for looking at vegetation health, and the visible bands, blue, green, and red, are really multi-purpose, with the shorter wavelengths like blue, good for looking at water constituents. And I'll show some examples of that in a little bit. Now, the beauty of that is, we look at, the full multispectral record with statistical procedures to identify and characterize features. We can also combine bands, any combinations of it, like these two examples, to try to identify or visualize particular features on the Earth. In the case of the image on the left, the false color band, that allows us in red to see the vigor of vegetation, whereas if you're more interested in seeing it as the eye would see it, this image on the right simulates it in a natural color sense. I'll give you just a couple of examples of imagery over a portion of South Africa, in this case in the Johannesburg region. This is in the most recent Landsat 8 image that was acquired July 25th of 2019. Again, it's 185 by 185 kilometers in its dimensions. It has 30-meter resolution, so we can, if we zoom into this, we can see resolve things as small as a 30 by 30 meter area. And again, this happens every 16 days. Now, with 2 satellites in orbit, we actually see things every 8 days. And so here is the Landsat 7 image on the left that was acquired 8 days prior to the July 25th Landsat 8 image. And the first thing this tells me is you've had a remarkably cloud-free period this winter. So, this is actually a pretty remarkable pair of images in which you have such high-quality images over the period of a little more than a week. But this process repeats itself. I'll show you a link on how you can access Landsat images, but these days, almost every 8 days, a new image of somewhere in South Africa is being collected, and generally within 6 hours of acquisition, you can download that for your particular purposes. Now, I apologize in advance for using a resolution example that caters to my interest in American baseball, but this is to just give you an example of what 30 meters looks like. On the right is the home field of my favorite team, the Minnesota Twins, and on the left, what Landsat sees on it. And so you see that we're not really resolving the fine structure of areas like this, and so in particularly complex settings, and this is one of them, you're really seeing a more generalized view. But if you think about the watersheds or the agricultural fields that are often much larger than this, we really are seeing things at a scale that approximates the scale of our management decisions when we are looking at the Earth's surface. Let me just talk a few minutes about our 3 most recent satellites, and then I want to talk a little bit about what's coming up in the future too. But a particularly important part of our history is a satellite called Landsat 5, launched in 1984, designed to work to function for 3 years, and it actually survived for 27 years. That durability and service earned it a place in the Guinness Book of World Records for one of the longest lasting Earth observation, for the longest lasting Earth observation satellites ever. There's a curious story behind this satellite, and that story is that when it was launched, the concept that NASA had is that it would be have the ability to have its orbit lowered so that it could be serviced by the space shuttle program that was in operation, from the 80s forward. And so to do those orbital maneuvers, it carried an excessive load of fuel. Well, when one of the early shuttles exploded on launch, NASA canceled the program to service satellites. And so Landsat 5 just happened to have a huge amount of fuel. And that allowed it to continue its design life approximating almost 30 years. Remarkably, most of the technology continued to work. There were some communication problems, and I'll show you, unfortunately, what the impact is. But, with the failure of Landsat 6 and some technical issues with Landsat 4, the long life of Landsat 5 saved the program and continued this global record that we now take such creative use of today. Right now, we have 2 satellites that are still functioning in orbit. Landsat 7, which was designed to last 5 years, in April of this year passed its 20th year of service, and it is actually running and collecting more imagery than at any point in its life, imagery from all corners of the globe. It has a technical glitch that means that 22% of every image is missing. I'll show you an example of that, but it's still high quality, very usable data that we rely on heavily. It is coming to its end. Ultimately, what causes satellites to terminate, if nothing else, is the end of the depletion of its fuel supply. And we are expecting next fall, our fall, your spring, in maybe October, November of next year, that Landsat 7 will be at the end of fuel, and so we will lower its orbit so that it can potentially start its process of moving toward re-entry into the Earth's atmosphere, where it'll burn up. Now, there's an asterisk on that, and that asterisk is that NASA has identified Landsat 7 as a target for a proof of concept refueling mission. What they would like to do is to send a robotic satellite into space that would rendezvous with Landsat 7, grab hold of it, drill a hole in its fuel tank, refuel it, patch up the hole, and then release it so that it can continue on and collect imagery. Final decisions are still being made on whether that's possible, but that could extend the mission life of Landsat 7. Now, I have to qualify that when you're using very old technology that has been around 20 plus years, running out of fuel isn't probably the most urgent issue. It could be a technical failure of some kind. Okay, I mentioned with Landsat 7 this data anomaly that causes the 22% of each image to drop out. Here's the Washington, D.C. area, and you see the black lines radiating away from the edge, the right side edge of the image. That's an example of the dropout. And so, no, you're not seeing everything, but with subsequent orbits, you see those gaps fill in. And while it's desirable not to have these kinds of issues, they do not negate the value of the data for natural resources, land and water monitoring. Okay, let me talk a little bit about our newest satellite, Landsat 8. It seems new to me, but it was launched over 5 years ago. It's the newest technology in the Landsat series. Landsat benefits from what I would consider evolutionary advances rather than revolutionary. We're fairly conservative in the improvements that we implement from orbit to orbit, largely because of the importance of maintaining that continuity of measurement across the 47-year record. But some of the big benefits of Landsat 8. the ability to acquire imagery is much better than we've ever seen before. Basically, we're acquiring every image underneath the satellite as it orbits. The data quality is considerably better. The electronics have improved to the point where we have far more precision in our measurements. That translates in the ability to quantify subtle conditions on the Earth's surface far more accurately. Increasingly important is that it's geolocation. The ability of each observation or pixel element to be placed in the exact right location, orbit after orbit after orbit, has improved to the point where every pixel is within about 12 meters of where it's theoretically supposed to be. That's really good. We're in the final stages of implementing a new processing strategy that actually is going to lower that to about 8 meters. So the geometric quality of our images have really grown. I think really important, though, is that there were a couple of additional multispectral bands added to Landsat 8. The coastal aerosol band, which was designed to improve the quantification of water column constituents. The cirrus band that allows us to remove clouds more accurately, so we're seeing the land and the water rather than cloudy land and cloudy water. And then a thermal band that was designed to improve our ability to calculate surface temperatures and therefore more reliably estimate things like evapotranspiration and water use. Here's an example of what an image looks like with the addition of the coastal aerosol band. This is a very short wavelength blue band. The shorter the wavelengths, the better the penetration of water. And so as you see from this, the fine detail of sediments and other constituents are more identifiable than they've ever been before. A researcher we work closely with, John Schott from the Rochester Institute of Technology, has done extensive field work that has concluded that with Landsat 8 now we can reliably measure things like chlorophyll, colored dissolved organic material, and suspended materials in freshwater bodies and nearshore areas. That improved geolocation has been a real plus for the cryosphere community, the people studying snow and ice, and in particular glacial movements. With that very high geometric location precision, we can actually trace changes or movement in ice sheets on a repetitive basis. And in fact, that along with the improved acquisition capabilities of Landsat 8 have made Landsat 8 a real critical tool in the last 5 years of documenting these significant changes in our ice sheets that are now occurring. And just a quick tangent, the value of Landsat in monitoring Antarctica has recently resulted in a decision to name one of the unnamed glaciers of Antarctica the Landsat Glacier, as a testimony to the role it and some other Earth observing systems have had in improving our understanding of a very fragile and dynamic part of our planet. Now, I'm in the middle of the United States. We have our primary receiving station here, but we also have ground receiving stations through our international cooperator network scattered around the globe. And so here is just a map of our current primary partners. The South Africa station operated by SANSA has been one of our longstanding and most valued partners. It's in a very important place where collection of imagery over Africa is particularly difficult, and so the importance of this station just simply can't be understated. It's a very critical part of our program and has been for many years. And let me just walk through some examples of what we've been collecting over time, and you'll see how the locations of stations become so important to us. Here is a map of the numbers of images that have acquired over every bit of the Earth, or every visible portion of the Earth that the satellite can see over the first 5 years of Landsat 8. And as you see, Landsat 8's very robust ability to collect imagery means we have dense uniform coverage most everywhere. The high latitudes in the north and south are weaker, and that's primarily because of short growing seasons and low levels of light that make imaging not as practical. But Landsat 8 is just simply pouring lots and lots of imagery into the archive. UX can access any one of these new acquisitions within 6 hours after it's obtained. Landsat 7 isn't quite as robust because of older technology like data recording and communications, but it's still quite good. And even if you look at your part of the world, there's pretty darn good coverage, and that's largely because of the significance of the South African ground station. Landsat 5, if we look at its lifetime, isn't as good in some parts of the world. And this is because one of the communications channels failed on the satellite, and so we really were limited in our acquisitions to areas where we could communicate directly with ground stations. And the tragedy of this is those high latitudes in particular do not have the quality of coverage we wish we had. And if we just go back to the early days, that multispectral scanner record on Landsats 1 through 3, again, there are some gaps, but many areas still have very good coverage. So, this gives you a sense of the density of coverage that you have access to. Now, the primary tool for accessing any of the 8.5 million images in our archive, which is on the order of 3 to 4 petabytes of data, is through a tool that's web-based called Earth Explorer. Here is the web address, earthexplorer.usgs.gov. You have to register when you do it, essentially get a login, but that is the extent of the bookkeeping required. All imagery are free. As you scan through the holdings of Earth imagery that you can get through Earth Explorer, you will see that not only can you get Landsat, but you can get a wide range of other types of imagery. And in fact, we've recently added Sentinel-2 imagery from the European Space Agency as a source of data that you can get through our archives system. Now, Mark mentioned at the beginning the switch in 2008 to free data. I think that is one of the most remarkable decisions we made in the program. I wish we had made it in 1972, but by making it in 2008 at a time in which we were moving into an era in which internet distribution capabilities, computing facilities, gave us a robust capability that, it was really unprecedented. We started a revolution in the use of Landsat. The critical thing is that Landsat became a tool for everyone. I spent my life studying land change as in a research mode. I can tell you that research budgets seldom grow. They generally stay either stable or shrink. And so our ability to buy imagery was a real barrier to what we were able to accomplish. We essentially were stuck using the imagery we could afford, not the imagery we needed. Now, if I'm a natural resource manager, the problem is probably even more serious. The budgets are simply low, and so having the ability to use imagery was difficult. But now with free data, we have the opportunity to use to take on investigations over larger and larger geographic areas and spanning the full temporal record of Landsat. That's pretty important. A couple examples of that. This is a study that I think is really amazing that was led by the European Commission's Joint Research Center staff that has gone through the entire Landsat record starting in 1984, that high resolution 30-meter record, and created a very detailed seasonal map of global surface water and characterizations of the dynamics. If you just look up global surface water occurrence on the web, you'll come to a terrific interactive database where you can explore anywhere in the world the dynamics of water at any point in time from 1984 to the present. It's just a remarkable, very valuable way of monitoring the changes in both seasonal and permanent waters. Similarly, colleagues of mine have been using Landsat to monitor global forest gains and losses, again, at 30-meter resolution so that we can zoom in anywhere on the planet, identify where forests are stable, where they're gaining in area or losing in area, and start understanding the driving forces that are causing both the positive and the negative aspects of forest area across the planet. Incidentally, this was the first research product from that study. The work has since been institutionalized through collaboration between the World Resources Institute, Google, the University of Maryland, and other organizations, and this is actually an ongoing, frequently updated product. So if you look at, if you do a search on Global Forest Watch, you'll be able to go to publicly accessible searchable databases to draw maps of any area you're interested in. A very remarkable activity. One of the big uses of Landsat that's really started gaining in significance over the last 8 to 10 years has been the use of the thermal imagery, those measurements of surface temperature or brightness temperature that are collected by Landsat, and to use those using energy balance techniques to estimate evapotranspiration and ultimately water use from space. And the Geological Survey, working with a consortium of partners all across the United States, are in the final stages of developing a national ongoing capability to develop ongoing evapotranspiration maps of the country that can be used by water managers and litigators that are dealing with water use conflicts and a variety of applications in order to improve the efficiency of our management of U.S. water sources. We, as happens in many other parts of the world, rely on Landsat as a way of monitoring the impacts of wildfires. Every wildfire above a certain size in the United States is immediately mapped as rapidly as possible following the ignition of the fire in order to track its growth, ultimately to assess the severity of the fires. Those severity assessments are used by the natural resources managers in order to develop remediation plans to improve the restoration of those areas to a productive status, and then monitor the recovery of the woodlands and grasslands over time in order to test the effectiveness of their remediation strategies and gain the knowledge needed to improve fire remediation overall. This is an operational activity we've been doing for about 20 years, and it just continues to grow in its significance, particularly as the frequency of our large wildfires increases. Now, if we look collectively at how Landsat data are used, it's a foundational piece of science because it gives us that concrete evidence on how our planet is changing. In keeping with the vision of Stuart Udall and William Pecora, it is addressing those management and monitoring needs that help us address environmental and economic security, public health issues, and so forth. It does that now because of free data, and so I think achieving that vision of the early identifiers of Project Eros is really coming into its age right now. But whether we're looking at scientific problems or operational issues, the needs are the same. We need a global perspective so we could look anywhere in the world. We need an unbroken record so that we can break it down in time. We need our data to be well calibrated and consistent so that we can compare, and ultimately access to affordable imagery is a critical need. Now, you know, as somebody that worked on the Landsat program for many, many years, our number one concern is mission continuity. We understand the importance of a long-term record, and making sure that record continues into the future that remains unbroken and viable for the wide range of applications is the biggest thing we are concerned about. Fortunately, recent commitments over the last 4 years by the United States government is resulting in more stability than we've ever seen in the history of the program. Through an umbrella activity called the Sustainable Land Imaging Program, NASA and the USGS have laid out a plan for the next 30 years with Landsat. The first step in that plan is the development of Landsat 9. It'll be based on very similar technology to Landsat 8. It is being built right now, and at this point, the launch of Landsat 9 is scheduled in December of 2020. And so that will give us, as we come to the end of the life of Landsat 7, Landsat 9 will kick in and will continue that 8-day coverage of the globe. We are also in the final stages this summer of defining the capabilities of Landsats 10 and 11. And so sometime later this year, the design of the next generation of satellites, which we expect will have higher resolution and better spectral coverage, will come about. Now, part of the centerpiece of our long-term strategy in the future is to deal with things in a more collaborative and integrated way. I suspect many of you are familiar with Sentinel-2, an absolutely sensational Earth observation mission that includes Sentinels 2A and 2B that are both functioning, collecting global data. By design, Sentinel-2 and Landsat are very compatible in their spectral characteristics. When we move to Landsat 10, we'll try to make them even more compatible. But what this provides us with is the synergy of operating as a constellation, both Landsat and Sentinel-2, that could get us to the point where we're getting 3-day, 30-meter or better resolution imagery of almost anywhere in the planet. And in some of the early experimentation of that, these are some research examples in which, using that much higher temporal resolution, seasonal resolution, we're able to map at 30 meters the very detailed patterns of vegetation phenology, of greenness increases and their rates of increase that help us understanding changing productivity of our planet as it may relate to forces such as climate change. So I'm going to end there and be happy to take questions. What I'd like to emphasize is the fact that Landsat really is, as my colleague Curtis Woodcock says, the Earth's free press. The data are free, they're objective, and they're long-term, and they give us an opportunity to start providing objective inputs into some of the debates we're having on what's causing the changes at a planetary scale. Finally, let me point to two websites. The USGS website will emphasize the operational aspects of the program, and in particular help you use and understand the data. NASA will complement it with stories on uses, applications, and technology. So I will end there, and if I can take any questions, I'd sure be happy to.
Thanks, Tom. This is Mark. I just wanted to add a postscript to your presentation. Thank you so much for all the work you put in. I obviously see all the updates you've made to make it relevant to today and to South Africa, so I certainly appreciate that. You did a phenomenal job of going over what was possible with Landsat. And anyway, I just want to thank you real quick.
Sure.
Great. So I see we have a few questions already lined up for us. We want to start there.
Are the questions to be read, or do I need to look for them?
I can start the first one. The first question we
Sure.
have is if we can detail the chemical and biological pathogen presence changes in waterways.
You know, if the question is, do we have the capabilities of doing it? The answer is yes, to an extent. Our ability to characterize a number of constituents, with the one that's getting the most investigation now, that related to harmful algae, I'd consider it a research product at this stage that's on the verge of being operational. Unfortunately, Landsat 8 really is the only one of the Landsat satellites that is optimized for those kinds of measurements. And so it's good as a forward monitoring tool rather than an historical investigation tool. But that's a pretty important thing. The U.S. Geological Survey, working with our Environmental Protection Agency, has a very aggressive research project that we're hoping will provide early warning of algae blooms starting in the next year or two.
Great. The next question we have is artificial intelligence or machine learning being used to improve the quality or speed of information output from Landsat? Is Internet of Things sensor data being used for ground truthing satellite data? And if you have some examples.
The answer to both of those is yes. In fact, right now, artificial intelligence has been a research tool and interpretation of Landsat imagery for a number of years. But I think it's finally maturing to the point now where we are close to being able to make significant breakthroughs in it. If there's one trend in Landsat remote sensing that's really taken over since people now have access to all imagery, is that what we're finding is that by looking at Landsat not as a point in time, but as a time series, through the use of machine learning and artificial intelligence, our ability to compare today to an historical trend in a pixel's life is telling us more detail about its condition, its use, its cover, and indications of the trend it's taking into the future. So I think we'll see huge advances in that. One of the great enablers of that is an effort by Google. They've established a system called Google Earth Engine, and that would be a good topic for the group to investigate. Google has our entire Landsat archive, and they update it every time we add imagery. And they have made an open access public commodity computing capability that allows users from around the world to share access and compute using Google's vast resources, a wide range of topics. The examples I showed on global forest change and on water dynamics were both done using Google Earth Engine. And so I think Google Earth Engine has done more to advance our ability to understand the planet than any other single move other than making Landsat data free. It's a remarkably important activity. The other one on the Internet of Things, crowdsourcing has become a very important activity in our field. Ultimately, all aspects of our work needs calibration. In other words, knowing what's going on in the ground in selected areas so that we can search for those phenomena elsewhere. And every product we put out needs validation or a determination of its reliability and its uncertainties. And the use of tools for community collection of information has become quite significant, probably motivated more so in Europe than in the United States, but it's an area that's advancing quickly.
Great. Those are all of the pre-submitted questions. We have time for one or two more. If anybody would like to raise their hand, we can unmute you to ask. All right. Okay, we have a new question. Besides Landsat, are there any new hydrological Earth observation missions planned from the USGS?
Not at a concrete stage of planning. We have been talking significantly about the need for additional thermal imaging missions. The role of Landsat in looking at things like evapotranspiration to help water management has become a very, very critical thing. And so we are exploring the idea of using small satellite technology and thermal imaging to increase the frequency of those kinds of measurements. There are instruments that do that have recently been established on the International Space Station that, while not a USGS activity, is an important input that's being used particularly by our Department of Agriculture researchers, and eventually that will advance our capabilities. Too early to announce anything on it, but the requirements that have been identified for Landsats 10 and 11 pay particular attention to the hydrologic applications area. And so I fully expect that we will see additional multispectral channels optimized for water studies. But that's probably 6 months out before we make any announcement.
Tom, this is Mark. I just might tag on to that. NASA has been doing some research and experimentation with attempting to measure stream flow. from space, but so far as I know, it's never really moved to an operational status, but I know they've done some experimentation and research with it.
Yep.
I might ask another question. So there's, a lot of talk about Google launching this phenomenal constellation of a lot of mini satellites. Do you have some knowledge about that and what they might be gathering, or is this strictly imaging, or what will they do with these mini satellites?
I suspect you're referring to the Planet Dove series of satellites, which is a venture that is putting literally hundreds of small satellites, well, microsatellites into space that are geared to provide relatively high resolution on the order of maybe 5-meter imaging that can be completely global in every single day. That is a program that I think many of us looked at with both curiosity and maybe a little suspicion as to its viability when they first started moving in that direction 5 years ago. As of now, I think it's turned into a pretty significant activity. The data quality doesn't meet the kinds of radiometric standards we look for in Landsat, but to the company's credit, they are now cross-referencing their imagery to Landsat to try to provide that same radiometric quality and consistency we offer. And the research examples I've seen from the program show that that daily look at our planet opens some remarkable opportunities for really understanding the condition of our lands. It is a commercial activity, though. There's a fee for the data. That's the one caveat I'd say, but I think it's pretty exciting.
Great. We have another question. Are there any products that have been developed by the USGS or NASA fusing data from Landsat and GRACE satellites for monitoring of surface and groundwater changes?
The USGS has a program to monitor surface water changes across the U.S. And in fact, I think, and I'd have to go back and verify that, I think we've started releasing some of the research products from that development activity. But it is limited to the lands of the United States. I am not aware of any move toward the use as it contributes to groundwater. I know researchers in the Western United States, particularly at Nevada University Desert Research Institute, are looking at the link between groundwater and ecological condition of riparian zones. But that's all I'm aware of. Mark, you might know more on that one.
Yeah, so the USGS is a user of GRACE imagery. GRACE imagery is available to you too, is free for use. But the scale of it is regional in nature. It's very difficult to get down to, so it works. It has potential, let's put it that way, for an aquifer. Again, what GRACE measures is a change in mass, or the pull of gravity, and it does it in a very interesting way if you're not familiar with it, by the orbiting of two satellites in tandem. And as they orbit the Earth, the distance between the satellites extends and contracts depending on the gravitational pull that it detects below it and on the Earth's surface. And so it is a tool that can measure regional mass change. Typically, the only thing it really can change the pull of gravity at a given point is the addition or subtraction of water. So as a regional aquifer may be depleted, for example, that can show up as a change in the pull of gravity, a lessening of pull of gravity, which then can be calculated into a depletion in storage change in terms of aquifer. We've got some good examples from California, for example. I always have trouble pronouncing his name, but Flaminglietti has done a lot of work with that, as well as a guy by the name of Matt Rodell. So you could kind of Google those names. But so the USGS, I don't think is fair to say is pioneering any of the GRACE work, other than we're using GRACE data like anyone else could to look at groundwater storage change at a few aquifers on a regional basis, and they're mostly just research projects.
Please feel free to submit any more questions or raise your hand if you'd like to be called on. All right, well, in that case, I think we're good to end. I'd like to thank our presenter, Tom Loveland, and Mark Anderson for your contributions as well. This has been recorded, and we'll be sure to share this recording with all attendees. Thank you all.
Thank you all.
Thanks. Have a good day.